Sir,
Thank
thank
you
you
much.
so much. You ran through an enormous number of ideas and projects there, so it's tough to know even where to begin. But I should mention that your website, you mentioned that a couple of times. It's evosci.org, and let me see. We did have a number of questions. Who wants to put their hand up to go first? Let me see. And I had the one that jumped out was Michael Boyd was asking if a black hole would be a Maxwell's demon. Michael, do you have questions? Oh, and I guess it would help if I allowed people to unmute themselves. There we go.
There you go.
Sorry about that, sir. Go for it.
Michael. Hello, Michael.
Hey.
How you doing?
So let me, I made some chat stuff here. Let me see, I had a couple questions here.
Yeah, but again, that was a remarkable presentation, Remi. Thank you.
Oh, thank you very much, Tim. I was honoured to give it. And I hope something comes out of this little team we have here.
Okay, here's the question. Okay, you were showing this entanglement experiment using two entangled photons. And my question is, wouldn't the entanglement take place at the electrons that produce the two entangled photons?
Yes. I mean, what entanglement is, I mean, many people, they come to me and ask me what entanglement is and say, oh, you've got an electron spin here, and when you measure it, the spin on the other one, it has some kind of force that goes across and spins it down. Not that. What entanglement is, it's correlation. When you have a joint system, yeah, you can't split it apart with the tensor. You can't split the tensor product of the systems apart. It's not factorizable. So what generates entanglement is a conservation law. So if you have two particles and they're subject to the same process generating them, and say it's energy, they will be correlated. I'll give an example of this, spontaneous down conversion, where you direct a laser at a crystal and you get two beams coming out at half the frequency. Well, they're correlated because it's energy conservation. You have other forms. You have conservation by momentum, either linear or angular. So yes, the system that generates it would be entangled. And if I remember, every atom in your body and the shells around me, the electrons around each nucleus are correlated, they're entangled. Yeah.
So my experience with the entanglement goes back into the 80s with what are called tunnel diodes that they use for, and they use this for making infrared detectors. It's a type of junction called a Schottky junction. And so what happens is you get this diode cold enough and it creates what I guess would be best called a standing wave. You know what I mean by a standing wave?
Yeah, they're amplifying devices, aren't they? They're used at microwave frequencies, tunnel diodes. I think it's metal.
Yeah, well, in this case, it's just it's an electro-optic device. And so the point is it would produce a photon on both sides, but they'd be the opposite spin because it's like a standing wave, one going like, you know, a sine wave, and on what's in the middle is the barrier. And the barrier is what you call an event horizon. It's a type of event horizon. So in electromagnetic, in the semiconductor, it's basically the barrier is what the junction is. So that led to my other question, which is about Maxwell's demon. So essentially, a tunnel diode is a type of Maxwell's demon.
I've come across this type of thing before. Where are you talking about rectifier demons? Rectifier demons?
Well, a tunnel diode is a type of rectifier, yeah. Yes.
Yeah, I wasn't too convinced because I think what might prevent them working is the fluctuation dissipation theorem, where if you get a fluctuation, it's automatically matched by the dissipation, and there's no net gain. So if you take something like Johnson noise from a resistor, yes, you'll get a voltage across the resistor, which is generated by the thermal processes, but you can't draw any power from that, even if you rectify it, because the power generated is just sufficient for the dissipation, hence the
Well, you can't really see this because of the thermal noise, like unless it's very cold. This is like below 50 Kelvin is where this is occurring. So basically the way you take care of the thermal noise is by cooling it down, okay? But the point I'm trying to make, and then you were talking a little bit about cold, this thing being cold, like the UAP being a cold energy source. So another example, what I was asking is a black hole. Black hole is basically, we don't know what the temperature of a black hole is, for example. Could be cold. If black holes, let's assume for the sake of argument, there really are black holes, because that's obviously controversial. But if there are black holes, wouldn't that be an example of a Maxwell's demon?
Okay, let me think about that for a bit. But just on your point about temperature of black holes, you have black hole thermodynamics, and the entropy of a black hole is set by its surface area, isn't it? And the temperature. So they do have a temperature as such. Now, what I do understand about these event horizons around a black hole, I think they call this the black hole no hair theorem, where all information is lost. I think the only things that can emerge from the black hole are charge. Oh, I can't remember the other ones, where the information isn't lost. So if you sent a bunch of charged matter at a black hole, it would take on the charge of what you're throwing at it. How would it be a Maxwell's demon? Are you suggesting that somehow the black hole can sort information and spit out higher grade energy? Maybe are you talking about pair production, something like that?
More like a jet. I'm thinking of the black hole as a place where all the energy basically is in sync with each other, where all the protons are singing and dancing to the same tune. Okay. And then a jet is where there's a release of energy and matter. And basically it's a loop. You have an inner and an outer event horizon. At the outer edge, matter, everything becomes energy. There is no matter. All matter is unstable. It's like radioactive materials that are like uranium and plutonium. If we got close to the black hole's event horizon after the jet was emitted, that stuff is all that matter is stable over there. It's not radioactive, it's stable. But when you get over to the outer edge of the event horizon, then it's all unstable, and all you have left is energy. And that's the void. And that's what we call the so-called vacuum energy, okay, is emptiness as opposed to matter energy.
Yeah. Okay. Let me just say, regarding black holes, they can have several event horizons. If it's rotating, it will have a different event horizon. I think that's called the ergosphere. Yes. Mm-hmm. As regards to what event horizons are, the generally accepted one is the idea that it's a path of no return. You cross it, you're not coming back. Yes. Where you lose information about what's happening on the other side of it.
Dynamically, I would say that's true. But if you treat it as like a diode junction, then no, that's not true. It's just a virtual thing. You can't see past the horizon. That's all.
Well, and I should let me jump in real quick because Mark has had his hand up for a while.
Okay, so let me let you go. Thank you for your answer.
Thanks, Michael.
It's okay. Where are you, Michael? Michael Ball.
I'm right here.
Oh, Mike.
Oh, okay. So I was just listening in on your bit about the Maxwell's demon. I heard from Jeremiah a while back that there's a device that was able to remove very small amounts of energy using a 2-diode system. Basically, if you look at heat, it's just movement back and forth. And if you can separate, movement in one direction and sort of force electrons in one direction, you would end up with an electrical potential that you can eventually take out. Problem is, of course, the high frequencies involved in Brownian motion or heat. So by using 2 diodes, they were able to get a very small potential out of like a hot sample, meaning direct heat to energy conversion. Have you heard of this? Looked into it?
I haven't heard of that one, but as I said, I did mention I have some reservations about the idea of diode rectifiers. I mean, that's just coming from me, but as I say, I believe the thing which limits them is the fluctuation dissipation theorem. What you generate, what you gain on the swings, you lose on the roundabout.
Sorry, if I could jump in really quick, Remi, I can speak to that briefly. I just pasted an article about that into chat, and this came out last year. Actually, it was listed in Science Daily, so I guess it's credible. My understanding of the article, I could be mistaken, was that there was a proof in the 1950s that you basically couldn't convert Brownian motion using a rectifier, right? Maxwell's demon using a rectifier in a circuit. And that proof was considered to be like inviolable, right? There was no way around it. It was a theoretical proof. But apparently there was a loophole where the proof only involved one rectifier diode. And so the Science Daily article was saying that when you use 2 rectifier diodes in a circuit, there is a way around that. And that was what was demonstrated, I think, in September. I think it was around September 2020.
I'll have a look at this. I'll have a look at this. I may have read this some point last year, but I'll have another look. Always willing to have my ideas changed. That's what it's all about, isn't it?
It's interesting. And then just today, and I don't have a link for this yet, I could probably dig it up. Remi, I thought this one might interest you. You were talking about entanglement. I guess there was a new demonstration just hit the news. They were saying that physicists have been able to measure an entangled photon without destroying it. It was non-destructive measurement of an entangled photon.
Yes, that's known about. That's weak measurements and so forth. Yeah, that's known about. But if you want to pass that one on to me too, that would be great.
let me find that one. And so I'm sorry, Mark, did you have anything more, sir?
Oh, I was just going to say that although there was minuscule amounts of power that was being generated, if anyone will take on the mantle of making, bringing the efficiency level of that up, we'd be able to eventually turn on the air conditioners in the summer and create electricity versus, sucking electricity out of the. Yeah, and that would really solve the world's energy problem. Imagine just cooling off the oceans in order to create the energy we need during the winter and whatnot.
The biggest problem, we're all wonderful people, but the biggest problem is the peer review system. It's really bad right now. I mean, Julian Swinger was saying 6 decades ago how he hated the system, how someone could review his papers, and he could not know who they were and have a face-to-face with them.
That's what we started APEC for. This is peer review. This is live peer review. I can pull out a contraption, and just like happened 2 weeks ago, Brian Sinclair pulled out his contraption and said, "Anyone, come at me right now. This is your chance." This is peer review. This is modern peer review.
We need more people like us because it's just too comfortable. The situation in the universities and things like full economic costing, where they've just handed it over to the bean counters. We need more people who stand up for their ideas, even though they are left field ideas. Yeah. And you'll just find many, many salary men. And unfortunately, industry and government funding are just enthralled to university. And we should really be living in an age like the Belle Epoque. If you look at the end of the 19th and 20th century, so many inventions funded by
the Mansfield Amendment.
Gentlemen scientists. Yeah.
The Mansfield Amendment is really the cause for that. In 1972, I think it was, They passed a bill basically stating that anything that goes against the norm cannot be funded through regular channels. So government agencies and even universities wouldn't touch any of this stuff with a 10-foot pole because it risks getting them defunded, and that's how they kept it secret.
We're our own, as a species, we're our own worst enemy as a species. We should be 100+ years on. For the rapid developments at the start of the 20th century, you should be much further along. Yeah. But I don't fight the system anymore. I don't bother with them. I hook up with people like yourselves, and we can have our own.
We're not fighting the system. We're just creating a new system.
Yeah, indeed.
So let me see who else has questions. There was Mark. Jeremy Reese. He was asking about scale when separating heat. Jeremy, and Jeremy's on YouTube also. I should see if he has any.
Hello, Jeremy. You've got your microphone off.
You're still muted, Jeremy.
Hey,
Hello, Jeremy. How you doing?
yeah, I was asking my audience if they had any questions for you, and everyone, if you have a question for him, you can shout out live. Just put it all in caps. But he was asking about what scale you were talking about with your heat dissipation thing. This was a question from someone else.
I'm an engineer by background, and I wanted to develop a system which would rival power stations. You'd have to look at the papers. I was talking masses of power generation. I was talking megawatts per meter cubed. So if you had a heat exchanger, imagine you had a huge tube like at a power station with all that enthalpy flowing into the conversion device. I was looking at figures of megawatts and more. Yeah, where's a will, there's a way. As I said, I got to the point where the cost of developing ferrofluid, lovely guy, Liquids Research, and Kevin O'Grady, really, really splendid chap, and Vijay Patel, who works there, really splendid people, but that's the cost of doing research. You try to use the system, try to use a peer review system and publication to put accolades on your research, but there comes a point where you realize it's not set up. And we have these stupid windmills in the Thames estuary. It's pathetic. It's just a bloody windmill, and there's hundreds of them. You can do better than that. There's a will, there's a way. But anyway, that's my answer. We're talking about megawatts per meter cubed power conversion rates once we have the system up and running with the correct ferrofluid. Yep. All right.
Yeah, I don't have any other questions. I'm trying to find like some of these are just off topic and not appropriate, so I'm not going to ask them.
Could you drop your YouTube channel here so I might see what's going on? I'm not aware of the questions.
Oh, yeah. I just looked as well. Now you might get feedback because it's live streaming, right? So that would be an issue. But
I see.
Yeah, it's youtube.com/alien scientist. Looks like we've got about 150 people. And let me just shout out to everybody who's on Jeremy's channel. About 150.
Here's the video
people
link right there,
stream.
and I just dropped it in the live chat. So you can go
Alien,
there.
Alien System, was it? Alien, I can't remember what the
Alien scientist. Yeah, and he just dropped it in there.
Excellent.
Yeah, and my only worry would be feedback because the YouTube is streaming, but it's actually a few seconds behind, I've noticed. So let me, if it's okay, let me go back to Michael. He's raising his hand again. Sir?
Hi, Michael.
Hey, so I'm curious, you had that little device that had the, that you were spinning and it had the little like L-shaped spokes
Yeah.
on it.
Let's find the slide. I'll put it on screen again in a second. Where are we now? Bear with me, Michael. Just finding the slide.
Take your time.
And I'll put it on the screen.
Let me know if I can help you at all with that.
You'll be right. I think I just got to share the screen now. Share the screen. Screen. This one. Are you seeing what I'm seeing at all?
Yeah.
Yeah. This slide?
Oh,
No.
it's not, your screen share isn't up.
What's happening now?
Oh, it doesn't actually, it doesn't look like it's
Oh,
shared.
I know. It's all right. I know what I've done wrong.
There we go.
Right.
Mm, Now you got to open up.
There we go. There we go. Can you see?
Yep.
Yeah, there you go. You got it.
Okay. Right, Michael. What was your?
So let's see here. Now these metal L-shaped things, those are like the spokes of the, and this is on a disc and it's turning, right? And
Yes.
and then in between there's a on the right there, you're showing a cross-sectional view of the metal disc that's above it.
Yeah, it's a cutaway diagram. I would have been better to sort of chamfer the edges to make it look
Well,
like a
no,
cutaway.
that's fine. So
Yeah.
now the little the whitish area, white with the blue stripes in it, that on that image, that's the dielectric.
Yes, the cross-hatched area, the hashed area would be the high permeability material.
So now my question is the charge, the stored charge, not the mobile charge, but the stored charge. Where is that? Do you consider that in the metal or in the dielectric?
Maybe maybe I didn't quite get the point across. If I go to the previous slide, this is the electrical joule of this system. So this system, you've got the electrets, the charged spheres, and in the middle you've got the solenoid. So you've got the magnetic.
The disc is made of what material?
Well, this would just be made of an insulator, something robust
So
enough.
the disc is an insulator, so say a piece of glass or something.
Yeah, or
And
plastic.
then you've got charge centers, basically, right?
Yeah.
And so the question then is, so in this case, is the stored charge in the little dots, or is it in the disk itself?
Now, the way Feyman set this up, he had to say the stored charges are in the little discs. So they could be something like wax.
So they're in the little dots, you're saying?
Yeah.
Not in the disk. Okay.
Not in the disc. Yeah.
Okay. So now back to the other slide.
Mm-hmm.
Now, in this case, though, you don't have those dots. You have these L's, right?
Yeah, it's the electrical
Okay.
joule.
And
So
then the disk is the dielectric again, correct?
Yeah, it's different this time. It's not exactly.
So again, the same question is the stored charge. I'm not talking about the mobile charge. I'm talking about the stored charge. Is it in the metal or is it in the dielectric?
No. I'll run it by you again. This is the exact electrical joule of this system. So magnet here, electric here. Go to this system. You have your capacitor on top. So that's the electrical system and the magnetic system around the edges. So it's the reverse. It's the flip of the reverse. Maybe I'm confusing the issue by showing.
So you're saying the disc on the right, which we're seeing half of, that's made of, that's the dielectric? That's not the...
Yeah, maybe I'm confusing the issue. Maybe
well, basically the question is, if you took,
let him finish answering, Michael.
out,
yeah.
okay, if you took the dielectric, if you could remove the dielectric, would it stop?
Yeah. No, it works fine. Maybe I'm confusing the issue. I was thinking ahead. Let's forget the grey bit in the middle. I added that on to boost the electrical field from the capacitor on top. But if it's confusing you, imagine it's not there. Just imagine it's white space. So it'll be the complete electrical joule of this system. So you're just reversing. Where you've got charges here, you've got a magnetic system. Where you've got a solenoid here, that would be the capacitor on top. It's the flip side. It's the electrical joule of that system, which I believe would be easier for me to make. Yes. Forget this if it's confusing you. Forget the half tone area. Forget this. Yeah. So it's just a simple flip side. electrical dual. Does that make any sense to you? Imagine, I'll try again. Imagine this part here.
So imagine that, so you're saying, imagine that the hatched area, the whitish hatched area wasn't there. Is that
Yeah,
what you're
just
saying?
if it's easier for you.
Okay.
I was just thinking ahead.
So yeah, that's fine. But then the metal plate on the top, that's still a dielectric though, right?
No, a dielectric. It's an equipotential surface. It's a capacitor plate.
Okay.
It's literally
So
just
there's 2 pieces of metal. So there's
Yeah.
2 pieces of metal with a dielectric between them of something. What is the dielectric
Well,
between them?
you could just use air. but
Okay, air is
It's
a
just
dielectric.
it's just
So
a plate
again, I
capacitor.
could use air. I could use air to ask the question. So
Well,
assuming
Michael,
that two
Michael, slow
metal-
down a little bit. You got to let him answer because I think you're
Okay,
over.
2 metal plates with air in between it.
hmm
Where is the charge being stored? In the metal or in the dielectric? In the
Well, when you say charge,
charge.
you've got a magnetic charge, so you magnetize these strips, as in this diagram down here,
Right.
and you've got electrical charge, which is the field is perpendicular.
Between
So
plates.
this is a plan diagram. So the field would be going down, the electrical field would be going down into the paper. It's just a plate capacitor sitting on top. This is a plan view of the device. Cutaway diagram here showing the plate on the top. So it's like a sandwich. It's like a sandwich, yes? Do you use that term, American term, sandwich? I always thought it was a
Yeah.
sort of pretty expression. Yeah.
But the meat's the dielectric, correct? And the bread is the metal.
No, both. Forget the dielectric for a bit. Forget the dielectric. Just consider the pole pieces. Yes. I'll just run you through some a little bit of EM theory. Imagine you've got a plate capacitor. When you charge it up, yeah, ignoring the fringing effects, the field comes straight down. It's perpendicular to the plate. The electrical field comes straight down. When you cycle the voltage on the capacitor, the magnetic field will circulate round, it'll be a circumferential around the axis of the disk. Yes, that's how it will come out via the Maxwell equations. What we're saying here is that when you're changing the voltage on this capacitor, the magnetic field will react against these magnetized segments here and make the disk rotate. It's the electrical dual. If we look at this system here, when you change the current in the solenoid, when you switch it on, you'll get a magnetic field coming straight up axially. So along the axis, there will be the magnetic field. When you change the current, you get a circulating electrical field. So when you switch it on, it will act one way. You switch it off, it will act the other way. It's this electric field which is reacting against these balls, these electric balls around the outside, making the disk rotate. And the spooky thing is, if it's just suspended in space, if it's in free fall, it will start to rotate without pushing against anything, apparently. That's the mystery of the Feyman disk. Yeah. So you could have the thing in free fall and have this thing switch on, and it will start to translate. When you switch the current off, it will stop rotating. What I'm trying to do is to try and make that a cyclical process where you don't have this start-stop, where you can just build up this very small effect and build it up so that when you switch off, you don't get the electric field. I've got here, one and two, cases 1 and 2. Switch on, you'll get the electrical field in one direction from the solenoid. Switch off, it will act in the other direction. If you can get rid of that, the disk will just keep spinning up, getting more and more torque, more and more angular momentum. Yes?
So it's kind of like magnetic hysteresis is what it sounds like. You know what I mean by that?
Not really, I can't see the connection. Magnetic hysteresis, when you've got a BH curve,
Right.
so H is your magnetizing field and B is your response of your material. When you
Right.
get hysteresis, initially it will start out linear in the linear region, then it will saturate. And when you take the field off, the hysteresis effect, if it retains its magnetization, and then you'll get that. Be good if I had a sort of writing pad. Hang on, I'll just 1 second. You might be able to get this on the camera.
Okay. Yeah, and then pretty soon I have more questions to take as well.
Okay,
so.
yeah, I appreciate you taking time to answer my questions. I don't want to monopolize it.
It's okay. It's okay. Excuse the very bad drawing. I don't know if you can see that. Well, if I just scroll up and just see if I can find where. There we go. Is that coming through at all?
Yeah, there
So
we
that's
go.
kind of, yeah, that's the kind of magnetic hysteresis effect. So it starts off linearly, and then when you take the field off, it's retaining some magnetization. It's coming back. It's a hysteresis effect. Yeah.
Yeah.
Excuse me. I think I've slightly got that wrong. Excuse me. I think that's I'm missing out on coercivity there, but I'll have to revise all that.
Well, Remi, if it's okay, I'd like to move along to Mark Fiorentino. He had a question.
Hello, Mark. Hello, Mark.
Hello. I'm also interested in the Feynman disk. It looks to me like it's an electric motor of sorts. I'm interested in the efficiency of this device. Do you have any idea how efficient it is as compared to an electric motor?
Well, I have to say that the effect, the Poynting field effect on a singular cycle is a very meager effect. And if you look at the magnitude of it, I find, here we go. It's this constant. Can you see, am I
Yes.
still on the screen?
Yeah.
Yeah.
Permittivity.
Okay. Yeah. This is defining the momentum. If it's angular momentum, you just put a cross R in there. So you've got this very small constant, which is something down like 10 to the minus 11. I can't remember, 8.85 times 10 to the minus 12, something like that. So on a non-cyclical basis, so just a one-shot cycle, it's a very meager force. If you want to compare that to an electric motor where you've got the Lorentz force, or if you consider the force between magnetic poles, it's going to be minuscule. So this is why I'm trying to make it into a cyclical device where you can have this cycle going many, many times per second. Then it will add up and make a big force. Yes?
Yeah. Well, if it works and it gains momentum, then its efficiency will increase over time. True?
Efficiency. Normally when I think of efficiency, I'm thinking about energy and energy wastage and so forth. I think you're sort of talking about a figure of merit, aren't you? When you talk
the thing of you're putting some energy in through current, probably. I'm talking about the second Feynman disk, the one with the L-shaped devices, which looks a little bit like a metamaterial to me in some ways.
I haven't done the calculations, Mark. I'm at the stage of doing the theory just to make sure I'm not barking up the wrong tree.
I mean,
the only difference with
what you're saying is correct, eventually its efficiency would reach or exceed 100%, hopefully.
No, that's not.
If it doesn't, then
yeah. What I'm trying to say to you is, it's not like an electric motor. So you've got a drill in your hand. You switch it on, you feel a jolt in your hand as it's pushing against you to spin up.
right.
This thing would spin up in free fall. Yeah. Electric drill can't do that. It's not going to make a propulsion device for you in the vacuum of space. So that's the advantage to it. I'm not looking at this stage for efficiency, however you define it, by whether it's wasting energy, whether you're getting bang for your buck from it, whether you put a lot of point in.
I'm looking for it as a replacement or an energy generating device rather than for propulsion.
As far as I know, it wouldn't generate net excess of energy. I spent quite some time talking about the momentum and where it was being dumped to. I'm not trying to violate any sacrosanct laws of physics apart from the
Yeah,
second one.
conservation laws, right?
Yeah, because they're founded on very, very good principles to deal with, well, symmetry transforms in space. And what it comes down to on an intuitive level, if you're going to break the first law, you'd be changing the constants of nature. So for instance, if you have a brick, you lift it up, and then a million years later, when that brick is still held up, if the gravitational constant has changed, then the brick was, when you drop it, you're going to get more energy out than you put in. Yeah, that's what it amounts to. Violating the first law would mean violating the constants. The constants would not be constant. Momentum, conservation of momentum, is to do with the homogeneity and the isotropy of space. So every direction you look in, it's the same. I give this example for conservation of momentum. Imagine you have an athletics track. Yes, on the one side is a conveyor belt. So when you're running around the track, you can take it easy on the leg with the conveyor belt, because that would be a violation of conservation of momentum. You're getting a free ride on one side, or if it's a headwind or something like that, or is it a tailwind pushing you along? Yes, that's what violation of conservation of momentum would look like. Yeah. When they look up into the night sky, they see that space is the same. I know they talked, I think about 15 years ago, they talked about this axis of evil in space. I think it's around the time of the Second Gulf War, which was quite funny, where there might be an effect where space is not isotropic, but at least locally, we know that everywhere you look, up, down, left, right, back to front, space is the same. And that's the basis behind linear and angular momentum. Yeah. Does it help?
Yeah, I was just curious to see if this thing could be used for power generating. I'm interested in looking for new ideas for power generation.
Yeah, I keep an open mind once again, but I'd be very surprised if the first law wasn't broken. If it does get broken, I believe it will be something like somehow cohering 0-point energy, or some kind of what they call a fifth force. Yeah. It'd be something like that, but a lot of people tried. As Hal Puthoff and EarthTech said, they tried building these devices and they weren't able to rectify 0-point motion. I don't know, maybe they just weren't trying hard enough. I don't know.
Now,
bunch.
Remi, if I could ask a question quickly, one of the things you mentioned this kind of early on in your presentation, you talked about UAPs running cooled. And again, I've heard that in a number of these different experiments. But one thing I wondered, I don't have any firm thoughts on this. A few weeks back, Gary Stevenson suggested that UAPs might actually be upshifting infrared spectrum heat into the visible spectrum. And that was why it looks like, and again, I could be mistaken, but it looks like they are very dark on the IR scale of things, right? Like they appear just black against the outline of the planet. And then in the visible spectrum, they glow bright white. And so his suggestion was they're still emitting IR, but for some reason it might be getting upshifted. Do you think that might be the case?
Well, they talk about gravimetric effects around these devices. Somehow they've found a way of warping the space-time around them. If you take gravitational redshift, if I were to launch a beam upwards, by the time it got to the top of the atmosphere, it would be slightly redshifted because it's doing work against the gravitational potential. Now, if you have a reverse curvature, it will get blue shifted. So maybe that's part and parcel of the way these things work, and it could be it. I mean, I think if you can, and if he's not too irascible, try and get Jack Safati on. I laid into him a bit a few months ago about his approximation, using the linear approximation where he should have been using full general relativity. Get Jack Safati on, give him a slot, yeah, if he's willing to do it, and let him argue his case. Yeah, I'd be more than willing to do that. And if I have some time, I would like to try his ideas in the full set of the general relativity equations and see if they hold water. Once again, it's a very tiny constant. which not just me, as several people were pointing out, that you're not going to warp space-time with small amounts of energy, but he believes he can. Get him on one day, and I'd really be interested if you could do that, Tim.
Okay, yeah, I will try again. He and Keith had talked about coming on together, but the scheduling was just difficult for them. So, well, let me go to Alex next. And I should ask Remi, are you doing okay in terms of, I mean, do you need any water or anything like that, or?
Oh, I've got a little bit of water.
Oh,
okay. But this room makes the back of my throat tickle. There's some, I think there's dust in here or something.
Yeah, I just felt guilty. I know we've been going pretty heavy here, so I don't want to just grill you for 2 hours, you know.
Yeah, if you hear me coughing, I haven't got COVID. At least I haven't killed over yet.
Well, let me go to Alex next then.
Okay. Hello, Alex.
Hey, Remi, great presentation. Really a lot to think about here. I just had a quick question. It's a little bit tangential. I know you had been talking about like tachyon communication and violation of the no communication theorem. Can you talk a little bit about that and like whether, you know, if that were true, whether that would violate causality or not?
Oh.
Like where you could send a message to yourself before you sent it, you know?
I don't believe that. I believe, this is what I believe people are taking the Lorentz transform too literally. Yeah. I think I was on here a few weeks ago. Yes, it was. I was talking about a situation if you had bats in a cave and they're using echolocation. They've got some still vestiges of sight, but they've been in this cave so long and they're using this echolocation. They think it's the be all and end all of how you use metrology, how you measure your surrounds. And one day a group of cavers break in and they shine a light, and these vestigial eyes in these bats are saying, hang on, when I echolocate, I can now see that I'm dead reckoning. So by the time the sound wave has traveled and bounced back, in reality, the other bat or food morsel or some insect is not where it's supposed to be. And if you look at the Lorentz transform, it does have does have terms in it to do with time. Sorry, bear with me. I'm just thinking and doing it at the same time. Bear with me. I want to find the slide. There we go. Can you see that slide? Can you? Is it still on share? Yes, it's on share. Here's the Lorentz transform. So for the prime frame to the unprimed frame, prime frame. So that's for time. That's for space. So the gamma function is just the 1 over square root of 1 minus v squared over c squared, yes? Now, the second term here and here is the time retardation term. It's simply the time it takes from light to get from one point to the other. If you knock it out, you'd end up with these transforms. And I think I'd have to look at my history of science. I think these were what Lorentz originally proposed. Yeah. If you don't take this Lorentz transform too literally, you don't get these reverse causality effects, because let's try and think this through with time simultaneity. Yeah, imagine A and B are, I think they'd need to be vertical. No, I'd have to think this through. I'm not going to think about this on the fly, but the problem is coming from when you transform to different axes, that the axes don't stay perpendicular. Yeah?
Yeah.
They do this transform, and this is what a Lorentz transform looks like on the space-time diagram. And this is where all these notions of sending, yes, it is here, sending information back in time. If we look at A signaling B, yes, I've worked it out now. If we're looking at A signaling B, excuse me, if you project, so in A's frame, so imagine the unprimed frames are A's frame, it believes they're sending a signal to B. I shouldn't have really shown that as horizontal, because that's, well, it is showing superluminal. You'd be on a light cone. It's shown a superluminal signal from A to B. So in A's frame, everything looks fine and dandy. It's taking absolutely no time at all, and the signal arrives immediately at B. If you're in B's primed frame, you're seeing that A is in the future. So if you project across to this frame and then project B across, it's somehow sending information back in time, but it's an illusion because you're using this Lorentz transform with these time retardation terms on them. And if you could use a signal that's faster than light, you wouldn't be using this diagram, this space diagram. You'd be using this one. So I don't buy this idea that you're sending signals back in time. Yeah?
Yeah, makes sense. I was just curious because I heard you talking about it last week and, you know, sounded like you knew a lot about this. So thank you for answering my question and for a great presentation.
Thank you very much, Alex. Yeah.
Thanks.
Thank you very much.
Well, it is an
Michael.
interesting question because it brings up that idea of, I've heard several people ask whether UAPs might be time traveling or something along those lines.
More things under the sun, Horatio.
Yeah. Yes, sir.
Those UAPs are doing, I don't think we have all full knowledge. So I wouldn't rule out anything. I'm not ruling out time travel. Just, you don't see people from the future. Maybe these UAPs are.
HT Alvarez had a question, and I think he's been on multiple times. I think he has a bad connection, so I usually ask these for him. He was saying, and it's in chat, he's saying, thank you for your excellent and well-detailed presentation. In his 1952 Nature paper, Kulwick explains a similar idea about the EM pointing vector and dumping of energy on ZPE space. Mm-hmm. He's wondering what you're theorizing on using, let me see, dump the energy in ZPE space to create propulsion.
Right, dump the energy.
Yeah, I hope I asked that correctly. I should apologize.
I think what you're talking about is energy and momentum conservation. If you consider both systems, if you consider the ZPE system and the mechanical system as one entity, and you'll find that momentum and energy is conserved. Whereas if you don't, then it just appears a mystery. It's a bit like radioactivity, say, when it was initially discovered, and you would put something that just spontaneously generate heat until they understood the phenomenon and say, here's another term we need to add on to the energy equation, then everything's conserved. What you don't know appears to be a violation, but when you include it, then it's not a violation. So does that help?
Yeah, I think so. I think so. And let me see. He just thanked me for asking in chat, so hopefully he'll mention if he has more questions. But yeah,
I think Michael was a bit keen. He was asking. Yeah, here we go. So he was asking a question. Just if you permit, Tim.
Oh yeah, Michael, did you have another question, sir?
Yeah, I'm still working on that one I was talking about with the question about the magnetized metal versus the dielectric, and I have this short little video I wanted to show you that to give you, if I could share.
Sure. Yeah, if that's okay with Remi, you just have to slow down a little bit so we can answer you though. You were getting ahead of him.
That's fine. Here we go.
Or dissectable Leyden jar in this case. Leyden jar is just what the first discovered capacitor was called. First, to prove it works as a normal capacitor, I charge it up here with a Wimshurst machine. I disconnect it from the Wimshurst machine, and then I discharge it. From the spark, you can see that the capacitor was in fact charged. Now to show you the neat thing, I charge it up again, but this time I remove the inside plate. And then I remove the outside plate. I touch them together. Notice that there's no spark, nothing, which seems weird. You'd expect that the plates would have been charged. I pick up the original container, and when I put my hand inside, I do feel some prickly sensation on my skin, and my hairs react. Next, I put the capacitor back together. What do you expect to happen when I discharge it? A spark happens. How does it work? Let's look at a cutaway view of the capacitor. Each plate has charge on it in the area between the two plates. One plate is negatively charged and the other is positively charged. We can also draw a line between each pair of charges, representing the electric field. The closer the lines are together, the stronger the electric field. As we pull the inside plate out, the area between the two plates decreases. The negative charge on one plate moves to stay close to the positive charge on the other plate, and vice versa. That means the charge on each plate is more tightly packed together, and so the electric field lines are closer together. The electric field is stronger. And as we pull the plate out more, the area is even smaller. The charges on each plate are even closer together, and so the electric field is even stronger yet. The electric field gets strong enough to begin ionizing the air in between the two plates and the container. That's done by pulling negative charge off the negative plate. It's also done by pulling negative charge from the neutral atoms on the container, leaving positive charge behind. The container is made of an insulating material. It doesn't conduct electricity, so the charge can't get from one plate all the way to the other. Instead, it ends up on the container. This side of the container becomes negatively charged, and this side positively charged. Having lost a lot of the negative charge on this plate, it's no longer very negatively charged. And having gained negative charge on this plate, it's no longer very positively charged. So the act of pulling the first plate out of the container has caused most of the charge from the plates to be deposited on the container. And that's why you can remove the plates, touch them together, and put them back and still get a spark. There is another phenomenon called dielectric absorption. It means that the molecules in the dielectric will be rearranged as dipoles, and so a sort of charging happens in the dielectric. But that takes a longer charging time and charges up the dielectric much less than we see here. Well, thanks for watching. See my YouTube channel, rimstar.org, for more informative videos like this. That includes one on how to make low voltage capacitor.
Okay, so what I was trying to show there is that it's not the metal doesn't store any charge. It's only in the dielectric. Whether the dielectric's air or whether the dielectric's a vacuum. A vacuum is a type of dielectric.
Okay.
So the point I was trying to make is that it's not the metal. And in this, and I've also worked a lot with hard disk media, where you actually have a thin film of ferromagnetic material that you magnetize one polarity to the other. That's how your hard drive works. So it's not that. It's so the inertial effects I've observed have more to do with that the storage of the charge in the material.
Okay, I think there's some confusion here. I never did say that there was any electrical charge stored on the magnetic system. I called it magnetic charge. And also, you tend to find with most ferromagnetic materials used in a magnetic setting, they're like ferrites. They're specifically designed to not conduct electricity. They can't be equipotential surfaces. Yes?
Well, it depends on the polarity of, it depends on, so if it depends on the polarity relative to the moving charge. So if you have a positively charged magnet or a negatively charged magnet.
You mean
so
electrical or magnetic?
On the magnet itself, on the outside, so.
Yeah, that's quite possible for it to take a surface charge. It's an insulator. Yes, it can take a charge, but it's not relevant in the situation I'm describing. Yeah.
Okay.
Maybe offline, if you want some more help on this, I can explain more to you. But the best way to understand something is not to come with too many preconceptions, because they're going to load your thinking. You're going to be trying to push it one way where you want it to explain the other way. If you just take
how I
describe it,
I agree.
yeah. If you take how I describe it, then it will fit. It will fit in to your knowledge base. Do you have access to the Feyman lectures? They're online. I could. It's somewhere near the middle of volume 2. There's an awful good lot of of classical theory of electrodynamics in there. It's a good read, and it's at a level where it can take you from a sort of teenage student right up to about end of second year degree course, even the third year course.
Okay,
It's online.
thank you for your suggestion.
Okay,
Yeah.
well, thank you, Michael. So let me go to Jeremiah, and I think we're probably almost out of time then. Jeremiah, but welcome back, sir.
Hi, Jeremiah. Hi.
Okay, sorry, yeah, got myself unmuted. I can answer pretty much all those questions, Michael, about the Feyman disk. I studied it very extensively and have tried to replicate several different variations of it, and even tried to develop materials that trap charges to maximize the effect. So Feyman states a couple of important things in the lecture that are critical in order to make the thing work. First off, he states that the disk itself must be made of an insulating material, like acrylic, like fiberglass. It should be ideally a low mass material, and in the most ideal situation, there will be no disk at all. You know, just open space in a vacuum. Each individual sphere, the black circles around the edge of the disk, are all supposed to be hollow, very lightweight spheres on which you charge to a very high potential that cannot leak with no sharp points, and they are just resting on the surface attached to the disk, sort of to, you know, all keep them in relation to each other. So what happens is the field, when you connect the current from the electromagnet, builds up slowly over time. So the overall volts per meter that are radiated out from the acceleration of the charges within the wire as the current begins to build is a relatively small value, and as a result, the radiated flux that exerts a force, or a Lorentz force, on the charges that are trapped in each individual charged sphere is relatively small. However, when you disrupt the current, all of the forward momentum from the accelerated charges that had accelerated slowly over time and are now at a reasonably higher velocity suddenly stop. And that instantaneous change equals a very, very high volts per meter that only travels outwards from the now disconnected or open circuit electromagnet. And because that field is a space field that does not have anything to do with the charges any longer in the wire or with the coil itself, because it's effectively disappeared from the circuit now that it's open, and charges can no longer reflect from it because they'll just freely move around as if they were just in open air. What happens is the field travels outwards radially from the center of the solenoid electromagnet, hits the spheres that are charged, and exerts a Lorentz force on them that causes them to experience a slight angular momentum that was the difference in the change of velocity over time that the electrons took when they were already moving at a velocity v through the wire, and they suddenly stopped.
So it was because there was no power to the coil at that point. It's
because there was power to the coil
disconnect.
previously, and in originally the thought experiment, he says, imagine that the system starts out with current already flowing through the coil, and the battery is connected in the start of our experiment.
So you need a battery to start it. Once
He
you
suggests that you actually use a superconductor for a practical experiment, and that you let the superconductor go from a magnetized state in its superconducting state, where you basically place it down the center of a disk where it's already containing charged spheres. This could be done theoretically in a vacuum, where you have a superconductor that you can somehow cool down.
Shoot the magnet.
Has anyone made one that works?
And basically, you let it warm up and let it go from being supercritical to not. And during the transition, it'll automatically expel a tremendously strong flux that should exert forces on the charges trapped in the spheres.
The question is, did it work? Did your
Yeah,
experiment?
it's been replicated. It's not by Feyman, but by a couple of independent labs. There are a few papers that were replicated to show that there is a very small force. There's a problem, though. I want to point out a problem with this experiment, and it's one that almost everybody overlooks. Imagine that we have four large individual spheres. They're isolated from each other, but they're physically large. What happens to the charges that are trapped on the surface of the sphere, which normally would self-distribute sort of evenly across the surface of the sphere? Well, when the B flux from the radiated field that's angular, that means it's going to be just, pointing from, if you have a disc, it's going to be pointing towards, you know, the rotation of the disc. It's not going to be pointing outwards or upwards or any other direction. It's going to try to make the disc rotate. So because it's angular like that, you're depending on the amount of charge that you have trapped on those spheres, and you're also depending on that rate change over time. Let's see, how can I put this better?
Well, Jeremiah, we're almost.
Go ahead. Yeah, you know, maybe I shouldn't take all the time.
Yeah.
We can let's talk about this, Remi and Boyd. I'd love
talk
to
about this. Yeah,
because I have a lot more information and some papers and experiments that link to showing this demonstration operational. But I can tell you this: the larger the spheres are, the charges will move over the surface of the conductive spheres. So ideally, you want them to be as small as possible. Ideally, they be trapped ions so that the electrons that can move, that are mobile over the surface of any metallic conductors, can't move very far. Therefore, they have to exert their force to the disk instead of simply moving within the conductor.
Yeah, I get what you're getting at. Yeah.
Okay. Yeah. Well, let's do that.
Yeah.
Okay.
We'll talk later. Yeah.
Yeah, Michael too. Yeah, joining too. Yeah. Okay. Thank you very much. Yeah, thank you.
Wonderful. Okay, so I'm going to mute everybody out. Again, I'm going to put it back on gallery view. Again, everyone, please give Remi Cornwall an enormous hand. A very, very in-depth presentation, a wonderful Q&A session. I mean, just going through tons and tons of material. So thank you, Remi. I very much appreciate it, and I'd love to have you present again in the future if you're up to it. Okay, so now I'm going to go back to speaker view.